In the previous screencast, we took a look at how we can multiply two binary numbers. Effectively, it's the same as doing long multiplication in decimal, we've just got fewer times tables to remember. Simply put, we generate the partial products of the multiplicand and multiplier, then sum them to get our result. The only real complexity comes from keeping track of the carries when summing the partial products. The technique is pretty much the same for unsigned and signed numbers, we just need to perform a sign extension, but for the purposes of this screencast we'll stick with unsigned values. There are many different ways in which we can conduct this process in hardware, and in this video I'll be looking at the design of two major types of multiplier, shift-add multipliers and array multipliers. The fastest way to add multiplication functionality into a system that we already know would be to develop a shift-add multiplier. A shift-add algorithm generates one partial product per cycle and adds it to a cumulative total of the previous partial products. As we only need to perform addition, we could take our trusty ALU from last year and rewire it to allow this algorithm to be performed. For our inputs, we'd need one register for the multiplicand and the other to be fed back from the output, so we can keep adding on top of our cumulative partial products. We'd also need another register to hold our multiplier, and some control logic to get the whole thing to work. We start with the output register, or in this case the product register of the ALU set to 0, and read the first bit of the multiplier register. If it's a 1, we perform an add operation in the ALU to write that partial product to the output. This is then fed back to the input of the ALU, ready for the next operation. We then left shift the multiplicand register to increase the value by a power of 2, right shift the multiplier register so we can check the next bit and perform the addition again if necessary. It's much easier if I show this step by step. We'll multiply two 4-bit numbers, 1101 or 13 and 0110 or 6. We'll use a counter, I, to keep track of the number of cycles that have taken place. In our initial state, when I equals 0, the multiplicand and multiplier are loaded into registers B and Q respectively. Our product register, A, is empty. As the first bit of our multiplier is 0, no addition takes place, and therefore A remains the same after our first operation. However, within the same clock cycle, we left shift B and right shift Q ready for the next operation. For our second operation, the first bit of Q is 1, and therefore register B is added to register A. Again, in the same cycle, B and A are left and right shifted respectively, ready for the next operation. This shift-add algorithm is repeated until all values of Q have been checked, at which point register A contains our final product. This algorithm can generate a product within n clock cycles, where n is the width of the multiplicand. In hardware, this will be constrained by the width of the ALU itself. So the shift-add multiplier has the benefit of only requiring a small amount of extra control logic on top of our ALU, which could already be part of a system. This means that the design of a CPU would only require a few extra gates to implement multiplication. However, whilst n clock cycles per operation is fine for a small design, say a 4-bit CPU, would we really want to take 32 or 64 cycles to complete a single multiplication? Other multiplier designs allow us to complete a multiplication in one clock cycle, but use more logic elements to do so. The most popular of these is an array multiplier. If we look at the way in which we work out binary multiplication by hand, it's not too difficult to think of a different way to perform multiplication in hardware. We're just generating individual bits of our partial products and then adding them to generate each bit of our result. In fact, we could quite easily build a generic model for our binary multiplication by looking at exactly which bits are multiplied together to generate each bit of our partial product. We then just add up the results of these multiplications in each column to generate our final product. Any carries are just passed over to the next column. If we take a look at the truth table for binary multiplication again, we can very quickly see that multiplying two single bits together gives exactly the same result as just ANDing them. So in fact, we can conduct multiplication in hardware asynchronously. We just need a lot of AND gates to generate each bit of the partial products, and then wire them through adders to generate the final result. With this in mind, we can start building the RTL for our array multiplier. We'll do this by constructing each partial product in turn. As we've seen, to multiply two single bits together, we just AND them. So we'll look at our general model and create some AND gates to generate the first partial products. When we generate our second, we'll physically left shift it in our RTL diagram. This will help us when it comes to adding the bits up. I'll also add in some columns to keep everything in line. We'll use 1-bit adders to add our partial products as we go along, so that the RTL diagram doesn't get too confusing. Again, we take the reference from our general model to see which bits of the partial products need to be added together. We then link the line of adders from carry out to carry in to carry any excess values into the next column. Our last column on the left doesn't have a bit of the previous partial product to be added to, so we can just add it to the carry out of the adder on the right. We can then generate the next partial product and add it to the output from the previous line, cascading the final carry out down into the furthest adder on the left. Repeating this process for the final partial product gives us our complete array multiplier. All we need to do now is pass the sum from the lowest adder in each column to our output. In theory, this form of an array multiplier can perform an unsigned n-bit multiplication in a single clock cycle. Practically, this is dependent on the propagation delay through the array, something we'll be covering in the next screencast. The trade-off is the number of gates required to implement the design, so if chip space is an important factor, we'd need to evaluate the benefit of speed of calculation against the number of elements required to implement it. So how would we go about implementing this array multiplier in Verilog? Well, if we take a look at our final design, it's not that difficult to see. We only really need two different types of component, AND gates and adders. We could differentiate between full and half adders where necessary, but we might want to keep our design as simple as possible. If we start to think of our design in terms of a hierarchy, we can divide the array up into generic cells, which could be connected to build an array of any number of bits. One cell would contain an AND gate to create a single bit of any partial product and an adder to add it to the bit in the row above. The top level design would then consist of an array of these cells, with ports to input the numbers to be multiplied and to display the output. It may help to use this diagram as a reference when working through this session's lab tasks.